Today we are going to discuss about the topic Unit 5. Unit 5, gas turbines. Okay. So what are all the topics we are going to discuss in this session? That is, just I am going to give you an overview about it. So what is meant by gas turbines, where it is used, and what are the applications of gas turbines, and I am going to draw a simple layout for open cycle gas turbines and what are the components present in the gas turbine. This is what we are going to discuss in the today's session. Okay, so this particular topic belongs to the Unit 5. The title of the unit is gas turbines. Okay, basically what is gas turbines? Gas turbines is actually a simple internal rotary combustion engine. That is what actually gas turbine is called as. It is an internal combustion rotary engine. So this is what we used to call it as the gas turbines. Okay, so now why we are preferring gas turbines and what may be the advantages of gas turbines. Okay, so what are the basic concepts behind power generation? What are the plans used for, or what are the concepts used for power generation? That is the basic questions. First, I am going to answer this question. So we know that for power generation, we are having different types of power plants, namely steam power plant, or we can call it as thermal power plant, and tidal power plant. We know that hydroelectric, otherwise called as tidal power plant, nuclear power plant, and some other concepts based on renewable energy sources like geothermal, solar, etc. So these are some of the areas or some of the concepts which is used for the power generation. And why I said these things is that we are having a relation between power generation and the topic which we are discussing. So we are having another concept or concept or method of power generation is nothing but gas turbine power plant, which is based on the concept which is we are discussing right now. So other type of power plant is gas turbine power plant, and where we are having the application of the gas turbine power plant. That is the next question. Why we are choosing the gas turbine power plant? That is next question. Why? Okay. So the size of the steam power plant, diesel power plant, nuclear power plant, it is enormous. Whereas the gas turbine power plant, the size of the gas turbine power plant is relatively small. This is one advantage. And another important concept is it is self-contained. So this is another point which is related to the gas turbine power plants. So where on what places the space limit, that is space limitation, we can go for the gas turbine power plants. Some of the applications where we are using gas turbine power plants is avionics, propulsion and marine applications. So these are some of the applications of gas turbine power plant. And now I am going to tell you about how a gas turbine power plant works and what are all the major components of the gas turbine power plant. So I am going to draw a layout of gas turbine power plant. The gas turbine power plants or gas turbines can be classified into two categories. One is open cycle gas turbine power plant, and another one is closed cycle gas turbine power plant. Today in this session we are going to discuss about the open cycle gas turbine power plant. What are all the major components of open cycle gas turbine power plant? I will tell you while drawing the layout of the open cycle gas turbine power plant. Okay, it consists of it consists of three major components. One is compressor, which is coupled with the turbine on a same shaft. This is turbine from where we are going to produce the work output, And another important component of the gas turbine power plant is the combustion chamber. This is combustion chamber. Okay, so these are the major components. One, air compressor and combustion chamber, and another component is turbine. So how it works? So these are the major components of the gas turbine power plant. Components of the open cycle gas turbine power plant. Let me write it over here. First one is compressor. Second, combustion chamber. And third one is turbine. So these are the major components of the open cycle gas turbine power plant. Let me discuss how it works actually. So normally I'm going to give you stages. So this is, I'm going to name it as stage 1, and this point as stage 2, and this one as the stage 3, and this as the stage 4. So what happens at the stage 1, and what happens inside the compressor? What is taking place inside the combustion chamber, and what sort of things is happening inside the turbine? This is what we are going to discuss right now. Normally, the atmospheric air, it is drawn into the compressor at the stage 1, and it is compressed. It is moved on to the combustion chamber where the fuel will be injected, and the combustion takes place inside the combustion chamber, and hot gases produced will transfer to the turbine. As expansion takes place, we get the work output from the turbine. So this is how it simply works. So now, technically speaking, what are the processes involved in the cycle? It is, we can call it as Brayton cycle. It works on the concept of Brayton cycle, but there is some deviation. So we will discuss about the deviation also. Brayton cycle is a theoretical concept, but coming to the practical application, there will be some deviation. We will discuss about that, and what are the processes involved in the cycle. So I am going to write it down here. 1 to 2, first process. 2 to 3, second process, and 3 to 4 is the third process. I am representing or giving an idea about an ideal cycle which is called as Brayton cycle. Okay, but actually there will be some deviations. Okay, we will discuss about it, right? So the first process in the compressor, what happens is the process taking place in the compressor is isentropic compression process. 2 to 3 is constant pressure heat addition process. And last one, the 3 to 4 process is isentropic expansion process. So these are the 3 processes which we are discussing about the working of the gas turbine power plant, which is working on the concept of open cycle, ideal cycle, which is Brayton cycle, but we are speaking on the theoretical cases only. There will be some deviation. Let us discuss about the assumption and what are the things, what are the deviations. Okay, so I'm just let me rub it. I will draw the cycle separately on the right hand side top corner to discuss about the deviation. Okay, so we are having a compressor coupled on a common shaft with a turbine, a combustion chamber. Okay, so yeah, this is stage 1, stage 2, stage 3, and stage 4, which is a compressor. This is combustion chamber. I am annotating using CC, where this is the turbine where we used to get the work output. So 1 to 2 process is isentropic compression, 2 to 3 is constant pressure heat addition, and 3 to 4 is isentropic expansion process. Let me plot it in the PV diagram and the TS diagram. Okay, first we are discussing, keep it in mind, simply we are discussing about the ideal case only. Okay, so PV diagram and the TS diagram. Okay, so in Brayton cycle, ideal case or open cycle, there will be 2 constant pressure processes. Okay, first let me plot the TS diagram. So we said that the 1 to 2 is isentropic compression process, which can be drawn as a vertical line 1 to 2. Okay. Then next process is constant pressure heat addition process. So 2 to 3. This is constant pressure heat addition process. And next process is isentropic expansion process, which is 3 to 4 is isentropic expansion process. So this is the cycle. It is actually a open cycle, but we used to connect it. Okay, in the diagram. Okay, coming to the PV diagram. So 1 to 2 is isentropic compression. This is 1 to 2. Compression, as we know, pressure increases and volume decreases. And 2 to 3 is constant pressure. This is constant pressure. So constant pressure heat addition process. And 3 to 4 is again expansion process, isentropic expansion process. So this is 4. So this is how a cycle, this cycle, that is Brayton cycle, will be represented using TS diagram and the PV diagram. Okay. Now we are going to simply derive an efficiency for this, derive an equation for the efficiency of the Brayton cycle. So what I am going to do is, I am going to take every component, that is compressor, combustion chamber, then turbine. Okay. So I am going to apply the static flow energy equation. I am going to derive the efficiency of this power plant. Okay. So, and before that, let me tell you the deviation. So deviation. What is the deviation? So deviation in actual case. What may be the deviation in the actual case? So that is the next question. Okay. So here, what we are discussing here is every process, that is 1 to 2 is isentropic compression, 2 to 3 is constant pressure heat addition, and 3 to 4 is isentropic expansion. Out of these two processes, these three processes, two processes are isentropic. What is meant by isentropic? Isentropic is nothing but reversible adiabatic process. What is meant by reversible adiabatic process? Or else, what is adiabatic process? Adiabatic process means there is no heat transfer. What is mean there is no heat transfer? There is no heat transfer. How heat is generated inside a system? By means of friction. Okay. So if there is friction, there will be heat generation. If there is heat generation, definitely there will be heat loss. So what we are speaking? We are saying that the 1 to 2 process is isentropic compression process, that is reversible adiabatic compression process. Similarly, 3 to 4 is reversible adiabatic expansion process. But in practical case, that is not possible. Okay, there will be friction, there will be heat generation, there will be heat loss. So that is not practically possible. That is the first deviation here. Okay, so what is the deviation? First thing is no possibility, okay, for reversible process, reversible adiabatic process, reversible adiabatic process. There is no possibility. And next thing, pressure losses. We are speaking that the 2 to 3, that is heat addition, is constant pressure process. Practically speaking, there is no possibility for constant pressure heat addition process also. That is another deviation. But we are assuming that there is no pressure losses. That is another thing. There will be no pressure loss. So these are all the two deviations. Actually, there will be pressure losses. So these are all the deviation from the actual case. Now, how to represent the deviation in the TS diagram? That is the next question. So let me differentiate with the blue color marker. Okay. So what we said is that 1 to 2 is isentropic compression process. But what we said that the deviation in the actual case is that there is no possibility for reversible adiabatic process. That is, there is no possibility for the isentropic compression process and isentropic expansion process. That is what literally it means. So what happens? There will be some deviation. So I am representing is this using this pen, blue color pen, and I am marking it as 2 times. This is the first deviation. There is no reversible adiabatic compression process or isentropic compression process. Similarly, there will not be the presence of isentropic compression process. There is no reversible adiabatic expansion process. Reversible adiabatic expansion process. What happens is there will be some deviation. So I am representing this using the dotted lines in the blue color. I am denoting this point as 4 dash. So this is the case. Okay. So deviation. What is the deviation in the actual case? deviation from the actual case is there is no possibility for reversible adiabatic process. There will be pressure losses. These are the two deviation which is represented in the TS diagram for the actual case. Okay. So far we discussed about the ideal case. This is the actual cycle. Okay. So this is it. Now we are going to derive an equation for the efficiency of the Brayton. Okay. So what I am going to do for that, I am going to take every component and I am going to apply the static flow energy equation. And I am going to find out the work done by the compressor, work done by the turbine, and heat supply. Okay, that is what I am going to do right now. So we know static flow energy equation. Okay, the static flow energy equation is we discussed or we studied those things in the thermodynamics. So SFE. So just I am going to write down the static flow energy equation. Okay, static flow energy equation we use plus V1 square by 2 plus GZ1 plus H1 plus Q is equal to V2 square by 2 plus GZ2 plus H2 plus W. So this is the basic general static flow energy equation. First I am going to take the compression. Okay, so applying SFEE for compression. Okay, so I am going to take it for the compression. So simply, and there are some assumptions. What are all the assumptions? Assumptions. No change in KE, that is kinetic energy. There is no change in kinetic energy. No change in kinetic energy means there will be no changes in the velocity. So in such a case, we can neglect the V1 square by 2 and V2 square by 2. These two can be cancelled. And there is no datum difference. GZ1 and GZ2 get cancelled. And as we already discussed, the process is isentropic compression and expansion. So what happens is heat transfer will be neglected. So this is also get cancelled. So what are the remaining components? W, H1 and H2. These are all the remaining components. So we can write W by the compression, work done by the compression. WC is equal to H2 minus H1. Okay, we used to write it as H1 minus H2, negative sign. So work is given into the compressor. Okay, so simply I am writing like this. We know H is equal to Cp into T. Okay, we can rewrite this equation as Cp into T2 minus T. This is the work done by the compressor. Similarly, I am going to apply the static flow energy equation for the work done by the turbine. Okay, so in such case, again, what happens is V1 square by 2 and V2 square by 2 can get cancelled. GZ1, GZ2 get cancelled, and Q is also get cancelled. So the remaining components work done. Sorry, I missed the plus sign over here. Okay, work done H1 and H2. These are all the remaining components. So work done by the turbine is equal to, actually here in our case, turbine is working between the third and fourth stage. Okay, so what happens where the temperature will be high? Temperature will be higher at the third stage and lower at the fourth stage. So we can write it as H3 minus H4, which is equal to Cp into T3 minus T4. I am writing it for the actual case. So if it is for ideal case, what may be the, sorry, I am writing it for the actual case. If it is for ideal case, what may be the change? The change is T2 will be written as T2 dash and T4 will be written as T4 dash. That's it. So this is the simple change for the actual case. Now, what about the heat supply? QS, heat supply. We know the combustion chamber is working between third stage and the fourth stage. I am going to take the same static flow energy equation. Neglecting the velocity changes, V1 square by 2 and V2 square by 2 get cancelled. GZ1 by 2, GZ2 by 2 get cancelled. And there will be no work done. Since it is combustion chamber, work done is also get cancelled. Okay, so what happens? But there will be heat generation or heat flow will be there, right? Because it is combustion chamber. What is happening in the combustion chamber? Fuel will be injected, compressed air. The fuel will be mixed with the compressed air, and combustion takes place. So there will be heat. So now heat supply. So Q, H1 and H2. This is the remaining component. So Q, yes, heat supply. Where it operates, the combustion chamber. It is operating between the second stage and the third stage. Where the temperature will be high on the third stage. So we can write this equation as H3 minus H2, which will be equal to Cp into T3 minus T2. So the actual case is same, Cp into T3 minus T2. Now, what is the efficiency? We know, simply, we can say efficiency is nothing but output divided by input. Here, output is work done. Okay, so this is nothing but net work. And what about heat supply? That is simple, QS. We can say input is heat supply. So net work done, we can write it as WT minus WC and divided by, which is divided by QS. Now, I am rewriting this equation. I am going to substitute WT is equal to Cp into T3 minus T4 dash in this equation, and WC is equal to Cp into T2 dash minus T1 in this here in the WC, and QS is equal to Cp into T3 minus T2. That is what I am going to substitute here. So what happens to the equation? Let us check. Let's have a look at it. Okay. So work done with the turbine is Cp into T3 minus T4 dash minus Cp into T3 minus T2 divided by heat supply Cp into T3 minus T2. So this is the equation for the efficiency of the ideal cycle, actual cycle in a open cycle gas turbine power plant. Okay, so this is it. We know Cp is constant. Okay, actually I forget to tell you an important thing in the introduction itself. So we discussed about the open cycle gas turbine power plant. Okay, the open cycle gas turbine power plant, it consists of two components. One is compressor, three components. One is compressor, turbine, and the combustion chamber, where the compressor gives the power in order to compress the gas. You will get the power from the turbine. Okay, so in such case, what the turbine has to do? The turbine has to produce more gross work output in order to give supply to the compressor. Then only we can get a considerable or a reasonable net work output, which is W in ET, which is WT minus WC, which is divided by QS. Okay, and in the introduction itself, I discussed about the application of the gas turbine power plants. Gas turbine power plants are having wide range of applications like avionics, that is simpler airplane engines, and in marine applications for power generation in the ships, etc., etc. But considering the efficiency of the gas turbine power plants, it is having very minimal efficiency on comparison with the diesel power, steam power. Okay, so that is the case why people are going for cogeneration. Cogeneration is nothing but combining gas turbine power plant along with steam power plant. Normally, the efficiency range for a gas turbine power plant, it will lies between 20 to 30%. Okay, whereas in steam power plant, it will be from 30 to 45%. So if you combine gas turbine power plant and the steam power plant, you will get more efficiency. That is why people opt for cogeneration or combined cycle power plant. We can say it as combined cycle power plants. The term cogeneration is not that much apt. So we can say that as combined cycle power plants. Now, so that is the case. And another important thing is that there are ways to improvise the efficiency of the gas turbine power plants. So that is what we are going to discuss next. Okay. So what are the improvements which can be made for improving the efficiency of the gas turbine power plant? That is the next thing. Okay. So how? I'm going to give you an idea about it, and I'm going to wind up the class. The next session we will discuss about the improvements about or detailed discussion about improvements in the gas turbine. Okay, so there are three types are there. Improvements for increasing the efficiency of gas turbine power plant. Okay, so regeneration, reheat, and intercooling. Okay, so these are all the three methods by which we can improvise the efficiency, increase the efficiency of the gas turbine power plant. We will discuss about all these three topics in the upcoming classes in a detailed manner. Okay, thank you.